solutions video for the worksheet titled Mechanical Equilibrium Worksheet. For these problems, please use 10 for little g so that you can compare your results to the answers that were given. It also makes this easier, and AP Classroom, or I'm sorry, AP College Board allows you to use 10 on the exam. Math becomes a lot easier. So let's get started. Number one is a 25 kilogram bag that is suspended from the end of a uniform 100 Newton beam of length L, which is attached to the wall by an ideal, freely swinging, frictionless hinge, as shown in the figure to the right. So here's a hinge. The angle of the rope hanging from the ceiling is theta, and it's 30 degrees. What is the tension T2 in the rope that hangs from the ceiling? So we are going to have to add some forces to this beam. This is the beam right here. And the first thing we are doing is drawing, labeling, and drawing forces per our step by step. This is a hinge. So this is the force of the hinge. It is not broken down into components. I don't know what angle that is. There is a portion of that hinge force that's in the y direction and a portion of that hinge force that's in the x direction. Then we have force of tension that's pulling downwards right here. This is a force of tension, and we called it T1 because it's a rope or cable, and then there's a force called T2, and we know that angle. So if I were to redraw this, just to kind of clean it up and only show the beam, there's the beam. I've got T1 pulling down. I've got T2 pulling upwards at some angle. I have a force of a hinge at some angle that I don't know. And I also have the force of gravity acting on the beam, and that'll get located right smack dab in the middle of the beam. And that has been given to us as 100 newtons. This is the weight of the beam, which is also force of gravity. We know that the entire beam length is L. That's what they described it as. So this little piece right here is L over 2, and this little piece right here is L over 2. I don't know what L is. I may or may not need that at this moment in time. This is theta up at the top, which means this little angle right here is also theta. And I think that's all that was given. Theta is 30 degrees. So this, I could find the other angle here if I wanted to. That would be 150 degrees, but at any rate. So I want to know the tension T2. I don't know anything about force of the hinge. So I'm going to go ahead and see if I can sum the torques about this beam. And I'm going to eliminate that force from the hinge by putting my axis of rotation there. So all of its torque is no longer, because there is no torque caused by the force of a hinge when the axis of rotation is selected at that point. So if I were to do that, I only have, well, I have three torques. I have this torque from the 100 newtons, that's the actual weight of the beam, and I'll call that, maybe we'll call that torque 3, since I've got a T1 and a T2 over there. That will go in a clockwise direction, so that'll be negative. We'll go, this torque 1 is also negative, and T2 will be torque 2, and that will be positive. Now, what is T1, you're saying? Well, I know that this is all in equilibrium. This is hanging there. So I have a force of gravity acting on that 25 kilogram mass. And so 25 times 10 is 250 newtons. And if acceleration on that object is 0, which it is, then I know that T1 must equal 250 newtons. So I know T1. So that is 250 newtons. Don't know T2 though, and that's what I've been asked. So I'm going to sum all the torques. They will equal 0. I have one positive, it's torque 2, minus, I'll go backwards, see, torque 1 minus torque, I called it 3, and all of those have to equal 0. So let's start filling in what we have for torques. We have T2, or torque number 2, which is the force of tension. They called it capital T2. There's the force, times the distance away from the axis of rotation, don't know it, it's L, times the sine of the angle. between the force, so here's the force, and the displacement vector. So I have, this is my, or radial vector, I don't know how to say that. I can use either this angle or this interior angle. Both of those will give me the same value for sine because sine of, what is it, supplementary angles is identical. And one of those angles is theta, so I'm going to go ahead and say sine of theta, which they gave me as 30 degrees. Yeah, okay. Then I'm going to subtract, I'm running out of room already, torque from force 1, that is 250 newtons, times the distance, that is also L, times sine of 90 degrees, so I'll ignore that. And then I also need to subtract torque from force 3 from the 100 newtons, and that'll be 100 newtons times the distance L over 2, and that'll equal, oh, sine of 90 is 1. All of those added up will equal 0. I'm going to rearrange that so you can see what comes next, because to be honest with you, the first time I worked this problem, I didn't see it and went down a rabbit hole. Minus 250 times L minus 100 times L over 2 equals 0. Okay? Now, every single term on the left-hand side of the equation has L. In fact, it made me realize there was a flipping physics video. Whether you realize it or not, everyone brought L to the party. Even though the right-hand side of the equation has 0, I can divide L out from every single term. I can divide every single term by L. And in other words, I'm dividing the left and the right-hand side of the equation by L. Let me just do it that way. Okay, so I'm dividing every single thing on the left-hand side of the equation by L. Which means I have to divide the right-hand side of the equation by L. And so that means L cancel. So when you have something equal to 0, you have mass, for example, on every single term on the left, that's still the little song called Everybody Brought Mass to the Party. So we have T2 sine of 30 degrees minus 250 minus 150 divided by 2, so 50 equals 0. Now I basically take 250, add 50, okay, so I take 300 newtons, divide by sine of 30, and that gives me T2. So T2 is equal to 600 newtons. Everyone good? Hope so. All right, another problem with this hinge that we have, and this will be the last one that I do for you. Let's read it. 75 kilogram block is suspended from the end of a uniform 100 Newton beam of length L, which is attached to the wall by an ideal hinge. A support rope is attached at a quarter of the way to the end of the beam at an angle from the wall of 30 degrees as shown. What is the support? What is the tension in this rope they called T2? So we'll just come over here and draw this picture. I'm going to draw all the forces on it. I've got force from the hinge upwards, and until I get told to find something in the X or Y direction, I'll leave it at that. I have tension 2. This interior angle is theta, which means this inside angle I'll call alpha. And if theta is equal to 30, then alpha is equal to 60. So I'm going to go ahead and put that in there, 60 degrees. Then I have the mass of the beam. This is not a light beam. In other words, you cannot ignore it. The weight of the beam is 100 newtons, which is also equal to force of gravity. And notice I put it in the middle of the beam because they said a uniform plank or beam. And so this distance from one of the ends is L over 2 because the entire length is L. The other thing I know is that I have T1 pulling down on it. And if I go look over here, this is force of gravity acting on that object, and that'll be 750 newtons if I assume little g is 10. 750 newtons is T1, because those two have to equal one another since it's not accelerating. And I believe that's all the forces I have. We've been asked for T2. I'm going to use my axis of rotation at the point where the hinges, force of the hinges, because I don't know anything about it. And then I'm going to go through here and figure out, is this torque caused by the tension 1 positive or negative? That's negative. That's a counterclockwise direction. I'll call this torque 3, and that would cause it also to go in a clockwise direction. This would go in counterclockwise, so torque 2 is positive. So sum of all the torques is equal to 0. So I have 1 positive, torque 2 minus torque 1 minus torque 3 equals 0. Torque 2 is from tension 2, that's the force. The distance away from the axis of rotation, they said, was 1/4 the way, so that'll be 1/4 times L. There's the tension, I'm sorry, the force, the distance. Now I need sine of the angle. The angle between the force vector, which will be right here, and the vector from the R value is 60 degrees. So I'm going to put 60 degrees in there. Minus torque caused from the force 1, that is T1, which we know is 750 newtons. There's the force. Distance away from the axis rotation is L, and it's 90 degrees. And then I have to subtract the torque from what I called torque 3, which is 100 newtons, times the distance away from the axis of rotation, which is L over 2, and then again it's sine of 90. And all of those added up equals 0. Once again, I don't know L, but look, every single term has L, and I can divide the entire left-hand side of the equation by L. So I get rid of L, I get rid of L, I get rid of L, and when I divide by 0 by L, I still get 0. So just because there's 0, don't forget that is a case where everybody brought L or mass to the party. T2. So I forgot my 4. I got T2. I'll just go ahead. Sine of 60 degrees over 4 minus 750 newtons minus 100 newtons, and I got to divide that by 2, and that is equal to 0. So 750 plus 50 is 800. So I've got to take, yeah, sine of 60 divided by 4 is 0.2165. So 800 newtons divided by 0.2165 equals 3,695 newtons, which is what they said the answer was. In the following diagram, a meter stick is balanced in the center at the 50 centimeter mark. A 6.2 Newton weight is hung from the meter stick at 30 centimeters. As you can see, this is a meter stick. It's balanced in the center, so that's located at 50 centimeters. Meter stick, 100 centimeters, okay? How much weight must be hung at the 100 centimeter mark in order for the meter stick to balance? All right, so if we were to go ahead and think about all the forces acting on it, we have a force normal upwards from the contact of the pen. I'll do this in red. I have a force of gravity, which is the mass of the meter stick times little g. This is 6.2 newtons. They've already given that to me, and I have the force of gravity, which is the weight of that mass. So if I can find that force of gravity or the weight of that mass, I can then solve for m, hold on. That equals m of x times little g. Don't know the mass of the meter stick, don't know force normal. I'm going to pick axis of rotation right in the center and hope that'll eliminate those two forces from my torque equation. So I will sum all the torques. They will equal 0. We'll call this torque 1. Torque 1 is positive. I'll call this torque 2. And torque 2 is negative. So torque 1 minus torque 2 equals 0. And torque 1 is caused by the 6.2 Newton weight hanging on it. So I'm going to write 6.2 newtons. What is the distance that that mass or is hanging from the axis of rotation? At first, when I solved it, I did 30 centimeters. That's wrong. 30 to 50 centimeters is 20 centimeters. So that's 0.2 meters. And then that is sine of 90 degrees, and I'm going to leave that off. Minus torque 2, that's caused by the, I'll call it force of gravity from that mass X, which we don't know, but once we find it, we'll be able to solve the problem, times the distance away from the axis of rotation, which is 50 centimeters, since it's half the meter stick, so that's 0.5 meters, times sine of 90 degrees, which is 1. So I can solve for force of gravity that mass X is giving me, and that is 2.48 newtons. That equals the mass of X times little g. And so we can solve for the mass of X by dividing that number by 10, and I'll get 0.25 kilograms if I were to round to 2 sig figs, which is what the answer is in. The seesaw shown in the following diagram balances when no one is sitting on it. So that means that that fulcrum is right at the center of that seesaw. So the force of gravity is straight up. We got force of normal from the fulcrum. We don't have to worry about any of the other masses from the seesaw adding anything. It's balanced when people don't sit there. So let's keep going. The child on the right has a mass of 35 kilograms. So that is her mass times little g, which is 350 newtons, pushing downward on that. And she is sitting 2 meters away from the fulcrum. If the adult on the left-hand side has a mass of 85 kilograms, which will give a force downward of 850 newtons, if we multiply times little g, you have 10. How far should the adult sit? So I need to know this number. R equals question mark. The question asks for how far, so there's no doubt that it's a torque equation or question. So this one I'll call T1, torque 1, excuse me, and that will go positive, and this one right here will be, I'll call it negative T2. So the sum of the torques equals 0, so I'll say torque 1 minus torque 2 equals 0. Torque 1 is 850 newtons. That's the force. How far away? We don't know. That's what we're looking for. The angle is 90 degrees, so sine of 90 is 1 minus 350 newtons times the distance away from the axis of rotation, which is 2 meters, times sine of the angle, which is 90, so that's 1. And we'll solve for R, which is equal to 0.824 meters. Hopefully that one is straightforward. Here's a ladder problem, a little more challenging. We have 2 more to go on this video. A uniform ladder of 10 meters long and weighing 50 newtons rests against a frictionless wall as shown. A painter hangs a 5 Newton bucket 3/4 away up the ladder, so it's 7.5 meters from the bottom of the ladder. If the ladder is just on the verge of slipping when it makes a 50-degree angle with the ground, find the coefficient of static friction between the ladder and the ground. So I suggest drawing a ladder somewhere. This is smooth, so there's no friction. This has friction. We know that the ladder has a mass that matters. They told us the ladder weighs 50 newtons, so there's my 50 newtons. We have a bucket of paint that weighs 5 newtons, so we've got that force downward. We have a ladder that's touching the wall up top. That's force normal from the wall. There's no force of friction there because they said there's a frictionless surface. The ladder is also touching the ground, so there's force normal from the ground. The ladder wants to slip this direction, so if it doesn't slip, I have to have a force of static friction in the opposite direction, parallel to the surface. Force of static friction. The situation says that the static friction is at maximum because I'm just about to slip, and there's all the forces acting on the ladder. The distances I have some knowledge of. I have this distance, which is 5 meters, half the distance of that plank or ladder, excuse me. And I also know that this distance to where, let's see if I can get that. I know this distance all the way up to here is 7.5 meters. Okay. I'm asked for the value of mu sub s equals question mark. Mu sub s is located within that force of static friction max. That is in my x, forces in my x direction. So let's start there. Sum the forces in the x directions, that equals 0. And we have two forces in the x direction. Static friction max equals force normal of the wall. I'm asked for mu sub s, so let's go ahead and expand that. That is force normal of what? Force normal from the ground. That's where static friction is occurring. Force normal of the wall. So what do I need in order to answer this question? I need force normal from the wall, and I need force normal from the ground. So force normal from the ground is in the y direction. So let's sum the forces in the y direction. Those will be equal to 0. So force normal from the ground is up, minus 50 newtons down from the weight of the ladder, minus 5 newtons down from the paint bucket. All of those added up must equal 0. So now I know that the force normal from the ground is equal to 55 newtons. I've got one of the two things that I need. So let's now sum the torques. Let's go around and make decisions. I'm going to get rid of this force of static friction and force normal from the ground. I know the force normal of ground now, but I do not know the magnitude of the force of static friction max. I know that it equals force normal from the wall, but I don't know that value, and I don't have a way to calculate static friction because I don't know mu sub s. That's what we're trying to find. By picking that location, I've eliminated all those problems because that location as an axis of rotation means those forces there don't cause torque. They go right through that axis of rotation. There's no R value. So I only have a torque from this 5 newtons. I'll call that, and this 50 newtons, I'll call that maybe torque 1. That is negative. This I'll call torque 2, that is negative. This wants to go counterclockwise, so that's torque 3, and it's positive. So the sum of all the torques is equal to 0. So I have torque 3 minus torque 1 minus torque 2, and all of that equals 0. Definition of torque, force times distance from axis of rotation times sine of the angle between those things. So let's go over here and think about some angles. I'm going to use this picture over here. So this is 40 degrees and this is 90. So this must be 50 degrees up top. So we know that is 50 degrees. This is another triangle that I can create. So I know that is also 40 degrees. And the same goes for the force of gravity. That is 40 degrees as well. So now we have all those angles that we need. Okay. Let's keep going. So torque 3. Torque 3 is located at the force normal from the wall. How far away is it from the axis of rotation? 10 meters times the sine of the angle between those r vector and force vector, and that will be 50 degrees. Then I have to subtract torque 1, which is 50 newtons, times the distance away, which is 5 meters, times the sine of that angle between, again, let's look at it. Here's the r vector, and here is the force vector, so that's that inside angle, which is 40 degrees. Minus torque 2, which I called from the paint bucket, 50 newtons times 5, not 5 meters. This is 3/4 of the way up. That's 7.5 meters times sine of 40 degrees. And all of that equals 0. So hopefully I'm not going to go through every little step, but I solved it for force normal of the wall, and that will equal 24.26 newtons. I now have everything I need to solve. Force normal from the wall, force normal from the ground. 24.26 newtons divided by 55 newtons gives me 0.44. Let me double check again. 24.26 divided by 55. 0.44. There's my answer. There's no units. That's unitless. The problem that we did in our notes didn't have the paint bucket. It came out to 0.42. Now I've added an extra mass hanging from that. That static friction coefficient must be at least 0.44, which is greater. Otherwise, the ladder would slip. One more to go, then we're done. This is actually not an equilibrium problem, but I'm going to expose you. It's helping you see what's coming next. This is related to our next unit, and I feel like you can handle it. Two blocks are suspended from a double pulley as shown in the picture to the right, very similar to the apparatus I have in the front of the class. I have multiple radii I can hang different masses on. Radius 1 is 0.25 meters. Radius 2 is, where is that? 0.4 meters. So I know this value right here is 0.25. I know this is 0.4 meters. And they told me that block 2 has a mass of 3.5 kilograms. So 3.5 times 10 is 35 newtons. Where's the other block? Block 1. Why can I not find block 1? 2 kilograms. There it is. So that's 2 times 10 is 20 newtons. Okay. So what's the first question they want to know? What's the net torque acting on the system? The system being the pulley. Um, so this is going to be, I'll call it torque 1. That is going to be a positive. This is going to be torque 2. That is negative. And so torque net is the total torque. I have torque 1 minus torque 2 equals, torque 1 is force times the radius or distance away from the axis of rotation. You don't have an option. This is a pulley. The axis of rotation is right here. This is not in equilibrium. I'm going to accelerate angularly and linearly, actually. 20 times the radius away from the axis of rotation is 0.25 meters. This is also kind of gives students pause. What is the angle between that radii and that where that force is? That is 90 degrees. It will always be 90 degrees to that circle. So sine of 90 degrees, which is 1, minus torque 2. Torque 2 is that force, which is 35 newtons, times its radius, which is 0.4 meters, times sine of 90 degrees. I will then find that to be negative 9 Newton meters. What does the negative mean clockwise? Okay, counterclockwise is CCW. All right, so negative 9 newtons per meter. Now, what will the angular acceleration be of the pulley? Well, if I know the net torque, which is the sum of all the torques, I can find the angular acceleration if I know the rotational inertia or moment of inertia. I is essentially what I like to consider rotational mass. They call this inertia. It's similar to, if you think of it as the sum of the forces equals mass times acceleration. We're going to learn about I and why it's different than actual mass, but you haven't yet. But that's okay. We know that we can solve for the angular acceleration if I know the net torque acting on it and I know I. And I was given to you in the first part of this problem, and I'll go look at it. It was 1.5 kilogram per, not per, 1.5 kilogram meters squared, and you'll end up with radians per second squared. If break open that Newton as a kilogram meter per second squared, you'll see that. And my answer is that'll be a negative 6 radians per second squared. So we're going to accelerate at a rate of 6 rads per second squared. Since it's negative, it'll be in the clockwise direction. What will the linear accelerations be of blocks 1 and 2? So if you can imagine, I'll just point at object 1. So here's block 1. This is accelerating downwards. This string is accelerating downwards. This string is accelerating downwards at that location where it touches the circle or the apparatus. We know that the linear acceleration is equal to the radius times the angular acceleration. It also, yeah, so all I need is the radius for point 1. All right, I wrote that wrong. Let me restate that. The linear acceleration is the radius for block 1 times its angular acceleration, which we now know. So I can find that. Acceleration linearly for block 1 is the radius, which was 0.25 meters, times the angular acceleration, which we found to be 6. We can use negative if we want to. They didn't ask for a magnitude, which they should have. And that would be equal to negative 1.5 meters per second squared. And actually, that is going in the counterclockwise direction. This actually determines the magnitude of that, and I should think about that for a minute, but that is 1.5 meters per second squared. That I know for a fact. The acceleration for block 2 will be 0.4 meters. The angular acceleration is the same for both blocks because the entire object is rotating, 2.4 meters per second squared. That is the answer to the question. That is it. Come see me if you have any questions.